Foundations. Now, I was recently reading The Three Little Pigs to my daughter. And, those pigs just built those houses right on top of the soil. No subsurface exploration, no geotech report. And, I told my daughter, why doesn't the wolf just wait it out? He should just save his breath, let the pigs build those houses. They'll have some serious settlement issues, structural damage. The function of those houses is going to be horrendous. The pigs are going to abandon those buildings, and the wolf can just eat them then. Now, my daughter was not amused, but she wasn't seeing the bigger point, that performing that subsurface exploration, getting that geotech report, properly designing foundations is critical. And that's where we're at in the stage of this course. So if you recall from the last class, we reached the bottom of the excavation, and this, from a risk perspective, was great because that meant we were able to retire a lot of the risk that we had and a lot of the contingency that we had set aside because maybe we didn't hit utilities or existing foundations and a lot of our subsurface risk was gone. But we're not out of the woods just yet. Foundations, of course, are subsurface. They're embedded or installed in the ground. And so once we get to the end of this class, then we can really breathe a sigh of relief. So the responsible parties here, of course, we've talked about the geotechnical engineer quite a bit. They determine what soils are present and predict the behavior of those soils. But the structural engineer takes it from there, and they design the foundations based on that criteria. This scope falls under Division 31 primarily, which is earthwork, but portions of this scope could be in Division 3, for example, under concrete. So in this class, we'll talk about the different foundation requirements. What exactly does the foundation need to do for us? And we'll talk about the two different types of foundations. They fall broadly into shallow and deep foundations. So what are the foundation requirements? The photo on the right shows a drill rig drilling a hole ultimately for a caisson or a drilled pier. Ultimately, what are the requirements of that drilled pier? First of all, it must transmit the structural loads or the loads from the structure above down into the rock or soil. Now, unless we're building this building in space or on the ocean, we need to transmit the load to the soil. Let's assume that's the case. And the foundation must not settle so much that we have structural damage or we impair the function of the building. This could be differential settlement or uniform settlement. And it must be economically and technically feasible. So if we're on one of the coasts and we have a whole bunch of sand before we get to bedrock, we could probably drive a pile through that sand all the way to bedrock. It's probably technically feasible, but it might not make sense financially. Engineers could design the biggest, beefiest foundation in the world, but it hits the pocketbook quite hard, and we need to make sure we're watching costs. And it could also be technically very challenging if we tried to do that, and maybe it's not the right option. There's many other options in that case. And in the process of installing our foundations, we can't adversely affect adjacent structures or utilities through vibration or undermining them. So there's two main types of foundations, like I mentioned before. Shallow foundations is the first one. Shallow foundations transfers the load above from the structure to the earth below through either columns or walls. And a shallow foundation is usually used with residential construction or light commercial construction, to where your loads are relatively small and your soils can handle those loads. As far as terminology goes, if you have a wall and it's bearing down on a footing, you would call that a strip footing. Occasionally you might hear someone call it a wall footing. If you have a column bearing on a footing, you would call it a spread footing, or possibly a column footing. Now what's happening here is you have a load being applied to the footing, a force being applied to the footing, and the force is being spread out over a larger area. The magnitude of the force is then less. The pressure on the soil is then less. And you could picture walking out over ice, and if you're walking on ice and you're wearing snowshoes, you're in better shape than if you're walking on ice wearing high heels, if that's your type of thing, because the magnitude of the force is much less. In the snowshoe scenario, we've distributed the force over a greater area. Here's some examples in practice. On the left, you see your strip footing. The wall is bearing down on the strip footing, and on the right, same scenario. Now, we've mentioned before that some jurisdictions allow you to use a rule of thumb to design these strip footings. I'm not a huge fan of that. I'd rather do the geotech report and design my footing appropriately based on the existing conditions. Here's an example of spread footings. Again, the column bears down on the spread footing and is distributed over a larger area. Shallow foundations formwork is relatively simple, so you don't have to do a whole lot of excavation to get to the bottom, and you can just use plywood like you see here, which is stood up and held in place by steel rods. Ultimately, this will be filled with rebar and then poured with concrete, stripped, and then you have your shallow foundation system.